Hi everyone. Today Francisco Gancedo, who's a member of the Institute, will speak about the evolution of coherent structures in incompressible groups.
So thank you for coming. And also thank you, the organizer, for giving me this opportunity. It's great to be here. So today I'm gonna talk about different topics in my research. So more than being kind of giving details, I prefer to give you several topics in which I'm interested in, giving you also some results. So please, if you want more details, let me know, I can explain. If not, later with a cookie, I'll be very happy to give you even more details. Okay, so first I'm gonna talk about interface dynamics. This is what I mean by coherent structures. So let's think that we have two different fluids and then an interface between them, and I want to understand the dynamics. And I think I'm gonna have time later. And also, instead of having interface between two-dimensional fluids or two-dimensional flows later, I'm gonna go to 3D and talk about vortex filaments. So my first topic is gonna be Stokes flows moving by gravity. And this is joint work with Rafa Granero in Cantabria and Elena Salguero at the Max Planck and Leipzig. Okay, so I pick let's say a photo for every topic I'm gonna talk about. The thing that I want to what ideas I want to pick from this picture is just that usually you have a very interesting dynamic. You don't need a fluid moving with a high speed or high velocity. This is some experiment that you can do easily at home, put water and then drop ink on it and then let the fluid moving by gravity. Okay. And this is what I'm gonna try to do with the question. Okay. So I'm gonna consider an incompressible. So I know that there are people from different fields, so please let me know if the notation or something you don't understand. So I'm gonna pick a two-dimensional incompressible fluid. U is gonna be the velocity of the fluid. This is the incompressibility. Sy is in space, t time. I'm gonna pick very basic equation, which is just the conservation of mass in dimension 2 rho.
Excuse me, in your example, you have three-dimensional fluid, and here.
Yeah. 2D. Yeah. Let's focus on 2D. Most of the thing I'm gonna tell about in 2D can be extended to 3D. Okay. So conservation of mass, and then I'm gonna model evolution by very simple equation, which is Stokes. Later, I'm gonna move to Navier-Stokes, but let's remove the acceleration into Navier-Stokes, and then we get the Stokes flow. In order to get rid of some physical constant, to make notation more simple, let's take viscosity of the fluid equal to 1, and let's being a planet with gravity equal to 1, and then this is gravity, this is the pressure, and this is the velocity in the equation. And with this system, I close my equations. Okay, the nonlinearity is in the conservation of mass, and then the fact that we have two different fluids is because of the type of solution for rho I'm going to consider. So let's say that we have here a fluid with density rho1 and here a fluid with constant density rho2. Okay, and I want to understand these dynamics.
I guess that's what you just said, that you're 0, 1, and the fact that you're multiplying by 0, 1, it's because with what you're writing after.
This is gravity, yeah, because this is gravity. We have gravity.
Oh, I see.
Pointing that. Okay, and this is the main force that is moving my fluid. Okay. Good. Let me understand a little bit the regularity or the equation I'm dealing with, because I'm considering compressible fluid, I can use or put get the velocity in terms of the string function, use Stokes law, and in terms also of the string function. And then if you wish, I can get rid of the pressure doing this is the perpendicular grabbing, or doing the rotational in this notation, and then this is the relation that they have for the velocity in terms of the density. So this is the inverse of the bi-Laplacian, okay? So my density is twice regular than my velocity, okay? Because here I'm integrating 4 times and I'm taking 2 derivatives, okay? Very good. So this operator is famous, is the Stokeless. You can get them, you can get it. And okay, you can recover the velocity using the Stokeless. And this kernel is given by this equation, this function over here. This is a matrix, okay? This is a matrix applied to this vector. And okay, as you see, this is the identity matrix times the logarithm. This is like the Newtonian kernel, okay, in 2D. And this is the other thing that I need to get an incompressible fluid, okay? So as you see, my Stokes growth logarithmically, okay, in 2D in this, and you know, this part over here in this matrix cannot cancel or cannot get rid of this growth. And then because of that, for example, in this case of situation, because I don't have compass support, or you can have some problem with this growth. In the literature, you also can get this thing, this problem in 2D as this 2-dimensional Stokes paradox. But I'm gonna get rid of this thing very quick, okay? Of this growth very quick. Because I'm choosing very different topics, please let me go fast into previous result. I can discuss with you if you want. But let's say that the Stokes moving by gravity, the result that the people do because of this regularity of the velocity in terms of the density, they have like a system result a la Judovich, considering decay of the solutions. Okay, here I don't have decay in this setting. Okay, and these are new tricks. So I'm gonna show you new tricks to get decay, and also I'm interested in understanding the dynamics of the interface when I have this particular, let's say, configuration for the density. Okay.
Do you have some boundary conditions?
No. Let's say I'm considering here the whole space.
Okay.
I don't want to deal with
No boundary.
So here, some people study boundary conditions. So you have this setting in a bounded domain or in a bounded strip, and then you have boundary layer situation because of the Laplacian and so on. Okay, but I don't want to consider all that. Actually, what I'm gonna do, instead of considering, I'm going to consider the whole plane, but I'm gonna put a periodic wave. Okay, so I want to repeat this configuration periodically. Okay, and I'm gonna have an interface given by this. Okay, that repeat like this periodically. Okay, so then one can try to consider the Stokes in this periodic setting in one direction. Okay, we couldn't find it. Maybe you can tell me, but we couldn't find it in the literature. We were even able to sum this explicitly in 2D. And then this is the particular configuration. If you, let's say X and Y are close to 0, then you find in this kernel the same type of behavior near 0, 0, near the point 0, 0, same time of singularity.
Oh, sorry, one question. So
Yeah.
the point is that now we are solving u equal to the order 2 operator you gave us, order minus 2 operator you gave us before, but this time rho belongs to is periodic with that.
In the x direction.
Okay, and you want also the solution to have the same period.
Exactly. Exactly. I'm imposing this condition. Okay. Okay, so then one can, I mean, we could get this kernel, because I have in the y direction I know periodic. Okay, I'm only periodic in the x direction. Then the growth that you see for this Stokes is even worse because, you know, for this type of kernel in the y direction, you see the type of growth that you see in 1D. Okay, so this is growth like absolute value of y, which is the growth that you find for the Newton potential in 1 dimension, right? But you see that in the Stokes, there is also interesting growth also. So, and here we are dealing with gravity, so the first component of this vector is 0. So, using the structure, just the structure of this, of the density of the gravity, and if we plug this in the stress tensor and then we use this vector form, then we get rid of some component of the Stokes, and then the Stokes has this shape. And if you look at carefully, you see that in the first component at the end, we get rid of the growth. And in the second component, there is a cancellation that cancels the growth. And at the end, this S tilde at the end is something that decays very good when y is big, and also the gradient of S tilde is in L1. And at the end of the day, so because of these properties in the convolution, we can get nice estimates for u. Okay. So then we can propagate regularity using just trajectories. We want the density to be conserved on trajectories, okay, because satisfies the conservation of mass equation. And then the gradient of x gives an exponential growth. Okay, we have bound for exponential growth. Later, I'm gonna show you. My intention is somehow give you solution that at the end grows exponential. Okay, finding this.
So you'll actually see exponential growth, you're saying?
So yeah.
You're gonna find exponential.
Yeah.
Even in the presence of gravity.
Even
with the presence of gravity.
Yeah.
Okay.
Yeah. For this interface thing. Okay. Okay. One can consider more higher regularity, C gamma or C1 gamma for the interface, which is natural thing. And then, okay, let's try to, if one trying to bound this regularity for the gradient of u in C gamma, then we can use Morrey inequality using 2LP. We are in dimension 2, so we need p greater than 2 derivative, and then we end up with this equation. Again, counting derivative, we have here, we are integrating 4 times, and here we have 2 derivatives because of this, and then these 2 because of the Stokes. So at the end, we are at the same level. This is a singular integral operator, okay? Good, one can go to and try to do Calderon symbol, which is very nice, but the configuration I'm showing you, and we don't have decay, okay? But this is not a big trouble, because if you see this operator applying to the density configuration, okay? At the end is the x derivative. So somehow we can write the density like let's say main density or compact support density, and then another guy rho bar such that the derivative rho bar is 0. So for example, I can put here density rho 1, then here density rho 1, density rho 2, density rho 2. Making this flat, I can put this behavior at infinity in rho bar, and then this derivative is 0. And at the end, the same velocity, we are going to get the same velocity with this compact support density, okay? And then apply Calderon Simon here. And now here, this guy has compact support, so this is not a big deal. We can bound this by the side of the second component of in the interface. Okay. And okay, at the end, one can bound high regular norms also with the L infinity norm of the density. Okay, so.
Sorry, so what's the assumption of rho then?
Sorry?
You were assuming that the rho is a constant outside
It's
the
a patch configuration. It's a constant density configuration. This is preserved by the equation because it's a transport equation and you move through trajectory. So this configuration is preserved.
Sure.
So you put it initially and this.
But so rho is something and then is 1 outside?
No, it's constant rho 1.
Yeah.
And downstairs, constant rho 2.
Okay, and then when you decompose these two as rho C and rho bar,
so this guy is, let's say, rho 2 here between these two things, 0, and rho 1 here. Then this guy.
because the derivative is only in X.
Exactly.
Discontinuity in Y.
Exactly. So when you take the derivative with respect to X of this guy, you get 0. So the velocity that is moving your configuration does not beat at the end of the day this guy.
Because so X is compactly supported and then you are in infinite Y. So where is
Yeah, I am in the whole domain. So in Y is infinite.
Okay. But in reality, it's only a perturbation like this, and then it doesn't. Okay. Okay.
Good. So I have global regularity. Very nice. I want to get more insight, having more result about global behavior of this solution. And then what I'm going to do is to get a contour equation. So an equation in terms of this moving bundle. Okay. So in each domain, I have this property for the gravity, so I can integrate by parts. And at the end, in the velocity, okay, with this configuration, at the end, I can get this contour equation. This is a trick with the Stokes giving us the velocity of the contour. Okay, so I have an equation just in terms of the contour. Okay. Oops. With the Stokes. Now I'm gonna do calculation get more and more complicated. So please believe a little bit the computation. So what we are gonna do to understand this contour equation. I mean, if you are into contour dynamics, this equation looks a lot like the Vortex patch equation for 2D Euler, but because this is like a logarithm, so you have here in the Stokes the logarithm structure. You also have this thing, but also you see here gravity. So the second component, gravity playing an important role in this non-local equation. Okay. What I'm gonna do there to understand configuration is to linearize around flat, which is a stationary state. Okay. So if I linearize around flat, so I'm saying that my curve is close to flat, linearly, okay? Then I get this non-local equation for the evolution of the linear flat equation, which is the inverse of the square root of the Laplacian operator the evolution in terms of the inverse of the square root of the Laplacian. Okay, so this operator is explicit in the periodic setting given by this. To analyze this, one can do Fourier, okay, Fourier transform, and then to solve the equation explicitly, this is what one can get, okay, for the Fourier mode. So we have preservation of the zero mode, and this is the important thing, depending on the size of this configuration, we see kind of exponential growth or exponential decrease. But an important thing here is just that for k very large, this is almost nothing, and it is not clear how one can get advantage of this. Not so clear. So at the end, this equation over here, what we see in this operator over here, what we like to call is like a very weak damping. We have a damping, but very weak, because we have integration here. Okay, but somehow what we see is an stable case, of course, when the denser fluid is below, okay, and an unstable configuration when the denser fluid is on top. Okay.
I'm sorry, can you, I'm not understanding, you're mentioning two fluids, but I don't understand even what's the equation we are considering to describe the two fluids.
Because I have two different densities. So let's say that here you have a fluid of density 1, and here downstairs you have a fluid of density 2. It's expressing the fact that your density has jumps.
Oh, I see.
And you have fluid of different density.
Thank you very much.
Okay.
And then in my mind, so rho takes two values.
Let's say 1 and 2.
Fantastic. Thank you very much.
And then the interface, you have this between these two different. Okay.
So are you mostly interested in the unstable case?
I'm gonna do both.
Okay.
I'm gonna understand and give you this exponential growth, understanding the stable configuration first. Okay. So let's start the stable case when the denser fluid is downstairs, and then what I'm gonna show you is stability of solutions. So let's start with interface which is given by a graph. Then we want to see how this is evolving. The equation is highly non-local with a lot of terms, but is given in the compact set that I showed you before with the Stokes. Okay. So, but at the end of the day, what we have is that the evolution of H is given by this weak damping term with the good sign, and then the nonlinear terms. Okay. What can we say? Okay, so with Rafa and Elena, let's put an initial data. We are not sharp because this is the first result of this type, so we are not sharp. For sure, we can get less derivative, but let's say that we have an initial data small enough, okay, within our regularity. Then we can have global solutions and then decay of these solutions. So if we consider these norms in which we have time in the L2, decaying time in the L2 norm, then we have this thing back, okay? And for that, we want to use this very weak damp.
So this just says that previous equation just says it goes to 0, right? I mean,
yeah,
like 1 over t squared.
Yeah. This equation, which is a solution of the contour equation that they give you,
Settles down, right?
which is also a solution of all these Stokes, conservation of mass and incompressibility. Okay. Good. I'm running out of time, so okay. So what I want to do is to check the evolution of this guy and to get an estimate of this type. So I'm gonna put this three bar norm, having L2 with a waiting time and then 3 derivative, and then try to find an estimate of this type, and then because this thing is small, then I can bound this for all time. Okay, so I do ML, and then what you have to do is to take advantage of this very weak damping. So if you go to Fourier, okay, is not difficult because of the decay of the exponential, saying that if we ask for more derivative, okay, then we have decay, okay? This is not difficult because of the exponential and the decrease of the, so if we ask for more derivative, we have decay. And then later here in Duhamel, okay, we have here two derivative. If we have two derivative, we have decay. One has to play a little bit with the norm that we are considering, and then integrate this guy, having some decay, doing some interpolation. At the end, for the L2 norm, one can get an estimate of this type. This is polynomial in this triple norm, and this is bounded. H3 estimate. In order to get the H3 estimate, we look for the evolution of this guy. This weak damping is integrating, but at the end is something positive. And then here, one also has to play the game between interpolating and having derivative. And at the end, when we integrate, having enough decay, we can integrate in time this guy. And at the end, we get this equation that we have, and then we have this global regularity or global system resolved with this decay. Okay. So remember that asking more derivative, I have decay. I can keep doing that. So what I'm gonna do is, what one can do is to ask for exponential or analytic functions for which you have somehow of exponential control for the Fourier coefficients, and then this gives us exponential decay. This is going to give us exponential decay if we ask for this regularity. Now we are going to consider exponential growth in the unstable regime. Okay, we're going to prove exponential growth. So the type of result we can prove is the following. You pick for me a time as big as you wish. I can find a solution that in the unstable regime grows exponentially up to this time. Okay, that you pick for me. And the way we measure the growth is with this analytic norm that now I'm going to show you why.
So what is it grows precisely? What is the object that grows?
This norm.
What is that?
This analytic norm. So let's say.
Oh, it's an analytic norm. So
yeah, this thing. So the solution that we find, because are in the unstable regime.
you have you got a growth there.
Exactly.
In decay, I see.
So our super nice solution. So we pick like super extremely nice solution in the unstable regime, and we can get them. Okay.
And that analytic, it'll still be analytic, but it'll grow.
Yeah. So somehow the S here is the amount of derivative, and then also this mu measures somehow the strip of analyticity in which your solution lives. Okay. Good. Let's go to, in order to get the solution, I'm gonna go again to the stable regime, okay? I'm going to understand the stable regime, and then later move to the unstable regime, okay? Okay, so let's be in the stable regime, and let's check the evolution of this nice norm, which is analytic, and I'm gonna make this solution suffer a lot, okay? So what I'm going to do for this solution is to decrease the strip of analyticity. I don't care too much to make this solution suffer. When you decrease the strip of analyticity, you get something parabolic. Okay, for this norm, this is the damping, which is more regular. The reason why I have here -1 derivative, and then quadratic. I'm going to consider also one derivative, and then decreasing the strip of analyticity, I am also making this kind of parabolic term. This is the damping. Now this damping is also important. I'm integrating once. This damping is also very important. And then cubic. And then here we have, I share derivatives, 0 derivative, 1 derivative, and 2 derivative.
What's the superscript of the A represent? I forgot that.
The amount of derivative. This is the analyticity strip. and the superscript, the amount of derivative.
Ah, yeah, okay, thanks.
Okay? Good. So then what? Then having my solution small enough, initially I can pick a way of decreasing the strip of analyticity. Okay, this is decreasing. Okay, I'm making all these quantities decrease. Okay, these quantities decrease. Because these quantities decrease, I can integrate them. And because I can integrate this, the weak damping, I can control here, if I integrate, how evolves the strip of analyticity. I'm having control of that. So I'm making, this is in the stable situation, my strip of analyticity is decreasing, but never collide, never collide. There is no collision. Good. Then what I can do is repeating the argument that I did before for Sobolev norm, but with this exponential growth in the stable regime. If you believe me, I can repeat now. I have this control of the strip of analyticity. I can repeat the argument. I'm having control of this. Then I'm done, because if I go backward in time, it is easy to prove that rescaling, you have solution of the unstable regime. Flipping the time is that as being in the unstable regime. Okay? So if I flip time, this is the way in which I get a solution of the unstable case. Okay? I have something that do not collapse. The strip of analyticity is decreasing exponentially. Going back, I'm making everything grow exponentially, and this is the way we get our solution with exponential growth.
So you mentioned something. So if you reverse time, it is kind of the same as moving from stable to unstable situations.
It's exactly the same, because if you look at this equation, at least at the linear level, if you start to go backward in time, it's just flipping. If I start to put time, negative time, it's like flipping the sign. And also here, if you put minus time and then take, you see that you change the. Okay. So and this is the way we get the exponential. So I'm very happy because you are asking me a lot, but somehow I have the feeling that I'm running out of time. So I wanted to show you stuff about the Muskat problem, also comparing with this situation, but I don't have too much time. The Muskat problem. So what I'm gonna do, I think I have time. I'm gonna sell you a little bit the Muskat problem. I'm also remembering you that this Tuesday, Eduardo Garcia Juarez, who is in the audience, is gonna give a talk on the Muskat problem at Princeton, my department. Okay, so you can, if you're interested, you can go there. I was going to talk about these two results, but I'm gonna tell you what is the Muskat problem, compare with the thing that I did before, and then move fast. I recommend you to go to his talk. So, what is the Muskat problem? It is about modeling. You see here water wave. This is not the Muskat problem. The Muskat problem model, the line that you see over here that separate the region, a dry region in a pulse media and a moist region in a pulse media. Okay? This is the Muskat problem. So the equations are incompressible. So we start exactly similar, very similar. Conservation of mass, very basic equation, and then the most basic equation to model a fluid in a pulse medium, which is Darcy's law. Okay? If you want to summarize a lot, Darcy's law is essentially telling that instead of having forces equal to moment to acceleration, what we have is forces, gradient of the pressure, gravity, equal to momentum. This is velocity. And the reason of having that is because you have a fluid moving inside a pulse medium. Okay?
Just a question, what mu represents
Mu here, it was going to be important because it's the viscosity of the fluid. So usually the Muskat problem is represented because you have two different fluid of different structure, immiscible fluid, and then you have, and you represent that because you have jump among densities and among viscosity. Okay. So instead of having here Laplacian U like before for the Stokes, we average somehow this Laplacian because we have the fluid in a plus media, and then this is the equation that we get. I don't want to do this with details, but let's say that at the linear level to compare is more singular because now we don't integrate that much the density, and then instead of having this base, the inverse of the square root of the Laplacian, when you go to at the linear level for the flat situation, which is stationary, is the square root of the Laplacian. So what we get is at the Fourier side is something similar, but instead of having t over k, is k, absolute value of k times t. So this is a parabolic equation with the square root of the Laplacian instead of the Laplacian. Okay. And then also you see a stable situation when the denser fluid is on top, and a stable situation when the denser, stable situation when the denser fluid is on top, and a stable situation when the denser fluid is below. So let me go fast on this. I wanted to show you a recent result, global regularity result for large solutions, but I'm running out of time. So I'm gonna focus as a promise on vortex filament results. And this is two joint work, one with Antonio Hidalgo Tornet at the Max Planck at Leipzig. And the first one, I'm gonna talk first about Navier-Stokes, and then later I'm gonna move to Euler, and this is a joint work with Antonio Hidalgo Tornet and Frank Mengual, both the Max Planck at Leipzig. Okay, so what is a vortex filament? So this is a very interesting or important question, but from the mathematical point of view, what I'm gonna do is to consider solution in which we see that the vorticity somehow is concentrated along a one-dimensional set. So you see this photo where you can see the vorticity concentrated here. Also, I would like to show you this video that I love. Make it. So what you see here, this is not fake video. This video was long time ago, previous to any artificial intelligence. So you see dolphin playing with somehow the structure that I'm telling you, in which you see the vorticity concentrated in somehow circles, or something which is close to circle. So they play with that, they even eat them. You see the circle structure and
This is not plastic.
sorry?
This is not plastic.
No, it's not plastic. No, it's okay. They can get it. They can get it. Okay. So let me play.
Is it pure water or there's air inside?
To be honest, I don't know.
When I had already spent.
I guess there's air inside, no? I mean, otherwise, how did they create it, I guess?
Yeah, but they made
must
it.
create it with some.
Yeah, but they made it. They made it.
Yeah, they made it so they made it with air because they breathe air. So
The dolphins made it? The dolphins made it?
Yeah.
I think so.
Yeah.
So it's like
Well, yeah, because they breathe air, of course, so.
For example, in volcano, you also can see also sometimes these huge small rings.
But not the dolphins,
Sorry?
but not the dolphins.
Okay, so let's go with the equations. Again, in compressibility condition, I'm gonna be in 3D, okay? And this first part, I'm gonna focus on Navier-Stokes, okay? And then what I want to study is vortex filament initial data, which is initial vorticity, okay, which is given by a delta function along a curve, a smooth curve, and with amplitude omega. Okay. This delta is just essentially we can apply this to a test function, very smooth function, and then we have this integral along a line. Okay, with amplitude omega. Very good. This is the type of initial data we want to consider for now.
So where is this vorticity directed on the loop? It's a loop, right?
No, here in this first Navier-Stokes thing, what I'm going to consider are ellipses, but later I'm going to move to rings. So
No, on the ring, at every point on the ring, is the vorticity tangent to the ring, or where is the direct vorticity?
So-
directed?
Tangent, yeah, I think so. Because you're integrating against the L, right?
yeah, and so you want the vorticity at any, so yeah, what you see, but what you see for this configuration is that your vortex rings is moving. You put a circle,
Yes.
so your whole
Vorticity is singular on the loop.
yeah,
Any point on the loop, where is the vector of vorticity directed?
So what you see here, it's not. I mean, if you put a tube, I'm gonna talk about this
Okay,
all this thing later with detail and carefully. But if you put a tube, what you see is just inside you spin a lot, okay, and then there is a matter about how this go to this configuration.
But
Okay.
why isn't the answer that the vortex, I mean, like your vortex vector is tangent to your alpha, right? I mean, from your formula.
The vorticity.
Yes,
Yeah,
that's what he asked.
Yeah. Okay.
So it's
okay.
tangent to the vortex. I mean,
Okay.
to the cycle, right?
Yeah.
Yeah, okay.
But okay. But the different thing is how. Okay. But I'm thinking, why are you asking this?
I was asking exactly that,
Okay.
because I know
I got-
it's tangent to the vortex.
Yeah.
Because every
It's like-
vortex
it's like
line
a vortex
has
line.
vorticity
Yeah.
directed to the local
Yeah,
time.
it's a vortex line. Okay, very good. So, what about Navier-Stokes and this configuration? So there is a explicit solution, which is nice because it is very nice to have explicit solution when you have the straight line. Okay, so you have a string line. Okay, then everything is more simple.
How is it different from the vortex line found by Burgers in the
Uh,
40s?
I don't know,
It is,
but
I think it's the same.
it's the same.
I think it's the same, yeah.
we're talking about-
Ocean is earlier than Burgers, though, I think.
They found that earlier than Burgers.
I think
I don't
so.
know.
Because
The thing-
Ocean is earlier, I imagine.
But what are you telling me about Burgers?
Burgers, I thought, published that sometime in the 40s of the previous century. And he used that to prove anomalous dissipation.
Okay, but for Burger, you're telling about Berger equation or?
No, exactly the same.
Exactly the same. Ah, okay.
Yes.
Okay.
Yes, exactly the same formula.
Okay. I have to look at. Okay, so hopefully this is early. I don't know, I have to check. But I mean, I know this in the literature, the Langevin vortex, in which you are flat in the x1 and x2 coordinates. And then this is just the heat equation, the heat kernel applied to a delta, initial delta in two dimensions, okay? This can be integrated and then get the velocity, okay? But here there is no too much geometry involved because for other usage, you put, for example, the circle, what you see or other configuration, what you see is that your vorticity move in the binormal direction. So you can do some trick or heuristic, assuming that you have solution. And then the velocity of the tube should move in the binormal direction with this law, gamma, the amplitude gamma times logarithm. And then you move the space. Placement is gamma t log t, okay? And also, if you want to see where the most of the vorticity is concentrated, what you have is square root of nu, the viscosity, and square root of t, okay? And this heuristic is gonna be important for the last part of the talk. Previous results. So if you put gamma small, then you can fit your solution into small initial data results for Navier-Stokes. And also there is a local in time well-posted results I'm gonna use from Bedrosian, Germain, and Harold Griffin.
Now, what are you assuming about your vorticity here? Do you have a curve or what kind of regularity?
Very smooth curve.
Okay, just any curve. This is regularity for any smooth curve.
Exactly. So the point, what I'm interested in is when the amplitude is big.
Right.
Okay, because when the amplitude is small, you can use this general theorem to have global system. Okay. And also very recently, Gallet and Svera described the dynamics, particularly when you have very short time dynamics, when you have the cycle. Okay, local in time. Let me go fast with this because I'm running out of time. So what I want to consider for this first thing is when we have this kind of configuration. So we have an helical symmetry initially. Okay, so
not a closed loop.
not a closed loop, this configuration for Navier-Stokes.
Mhm.
Okay, in which you know, when you see particles that spin in certain way and move in the z direction, then you have this property for the velocity, in which when you turn the angle for the velocity, then you find the same velocity, right? So this is called helical symmetry. I pick one, you can pick different velocity to the loop and also to go up, okay? And the point is just that the symmetry is preserved by Navier-Stokes, okay? So because of this helical interpolation, you can have these estimates, and then in particular, you can have global in time well-bounded result if your initial data is in L2 and a strong solution if your initial data have enough regularity, okay? What I want to study is when we have an initial data which is more singular, quite much more singular, which is this vortex filament, okay? And then in particular, initially, just because of the configuration, our velocity is not in L2. Okay. And this is the main theorem. So suppose that you give me any amplitude of the vorticity gamma, you have a smooth helical curve. Then you can have a global unique solution for the Navier-Stokes equation with initial vorticity given by this vorticity configuration. Okay. Okay, so in all, I was very fast with the bibliography, but this is the first global entangled point result without side restriction and without vanishing swirl. Vanishing swirl is when you do cylindrical coordinate and then the velocity in the angular direction does not depend on the angle. Okay. Here in this setting, we have vanishing swirl and still we have global regularity. Okay, what we do is the analysis in R2 and then the torus, okay, because somehow if we have this helical symmetry, we are going to repeat this configuration up and up, okay, this periodic configuration. And then it happened as before that when we have this setting, for example, the Biot-Savart kernel or the kernel that we have to use behave as in 3D near the origin as in 2D at infinity. So for example, if you have a very nice vorticity, this doesn't need to give you a velocity in L2, okay, finite energy. But okay, I'm picking this, I'm explaining you these spaces because they are not that standard and we are gonna use them. But okay, so L2 you lock, you have bounded balls. In L2 you have this control and also divergent free vectors, this dot 2 space in which you go to 0 to infinity. This is more technical. I don't gonna have time to go over these spaces or show you the technical details. And also this measure space that is, I'm picking this 3/2 essentially because this gives me a length longitudinal norm in this set of Borel measures. Okay, so essentially it's telling me that this measure is this integral along a line. Okay. Good. For short time existence, we work at the level of the vorticity, okay, with the Duhamel formula, and then we could prove that for short time we have a mild solution starting with this setting, and it is will continue in this space of measure. Let's say that the vorticity is in L2 with this wave of time, and also the velocity. We don't have L2 just because of this decay thing, but we have, this is just decay, okay? We have enough up to L6 integrability, okay? And this is, okay, this is for any measure which is X3 periodic, but the main important thing is just that if W is helical, if initially the vorticity is helical, it's gonna remain helical, okay? And what we do is we adapt Bedrosian and Germain Harrow-Griffin local system in this setting, and then Antonio main idea is to check that in this approach you go carefully and you can see that we can conserve the helical symmetry. Okay, so you cannot do unusual tricks like regularizing the initial data and try to pass to the limit, because this local system result is based, and uniqueness result is based on being, when you have a general vortex filament, when you do a transformation to the straight line, you have to be very close to the Langevin vortex. Okay.
5 minutes.
I have 5 minutes. Okay. So because I have 5 minutes, I'm going to run a little bit in all this detail. This is the local system. Then we have to do global, and global because of this L2 lack of decay. One have to do theory of weak solution for Navier-Stokes. We are losing for Navier-Stokes very helpful a priori estimating L2. So we have to do other trick with L2 log solutions. Then to finish, let me move to Euler vortex filament. Okay. So if we consider Euler instead of Navier-Stokes, now we don't have dissipation, and then one could try to go to Biot-Savart law and understand the velocity as we did before in terms of this non-local operator, in terms of the vorticity of. So this structure of being a vortex filament should be preserved, no, by Euler. Okay, one can try to plug this structure for the vorticity and try to see how is the velocity, and then check the evolution of the curve in terms of the velocity. But when you do that, what you find is that the velocity is infinity. And okay, it is not clear how to describe this curve. In particular, in this configuration that in Navier-Stokes is now well understood, when you have a cycle, what you see globally is that the velocity of the vortex filament has to be infinity. It has to move up with infinite velocity. Okay. So what the people do is what I was saying the other previously. So, but okay, now here you have to do some assumptions. You put a tube with certain thickness, and then you want to make this very, 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 very thin, and then to see how the curve is evolved. And then when you do some asymptotics, what you get essentially is that you have some big parameters that if you allow, this delta is the thickness of this tube. Okay, this delta is the thickness of this tube. So if you allow, so you're going to have some part of the equation which are very big. So if you assume that for short time you're going to be like this, and then you allow for a rescaling in terms of this thickness parameter, essentially what you get is this what is known as the binormal flow equation, and then the curve move essentially in the binormal direction times the curvature. Okay. But for that, you have to do some assumptions on asymptotics. Okay, this was done by the Rios. And these are some vortex filament mathematical results. Even the binormal flow dynamic equation has a very tricky dynamics. But also here, maybe I should mention you the vortex filament conjecture, which is if you can always find an Euler solution of this type for a general curve that at the end move with the binormal flow. This is not known. Well, 1 minute. Thank you. So in 1 minute, I'm gonna show you this last result together with Antonio and Fran, in which we give the first solution, Euler solution, starting from a circular vortex filament. So we start with this is a circle, okay? So this is a circular vortex filament with amplitude gamma. Gamma can be any. The solution that we find for Euler is a weak solution, okay? Otherwise, we have infinite velocity, okay? And there is many solutions. Our solution cannot be in L2 initially. It's in L2 minus always, but immediately goes to L2 and we have the energy decreasing, okay? The energy of this weak solution decreases. Very good. And what is very interesting for us is that the heuristic that I told you at the very beginning for Navier-Stokes is found in this Euler weak solution. So in particular, our velocity, so what we see is the Vortex ring getting thicker, evolving with the velocity that we get in the heuristic for the Navier-Stokes. And then here there is no vorticity, and all the vorticity is concentrated in this donut that is getting thicker and thicker as time evolves. Okay? You see that this is growing as with the Navier-Stokes heuristic, and then the speed, this h is how this thing goes up, is with the same velocity that I told you in the heuristic for the Navier-Stokes. I'm done with my time. Okay, so I don't have time to show you details, but at the end, the way is very natural. The way we get this Euler, this Navier-Stokes heuristic, we use convex integration techniques with the help of Fran and Antonio, and it's very natural the way we get this Navier-Stokes heuristic in the convex integration scheme. So with this, I'm gonna stop. Thank you very much.
Thank you very much. Is
there any
question?
Yes.
Have you considered the case of the vortex sheet bounded by the vortex ring? Like there is a velocity discontinuity in Euler limit. In fact, there is a finite vortex sheet also bound by Burgers and Townsend. So it is some hyperbolic tangent solution in the Navier-Stokes. And then on the boundary, there is this, again, Navier-Stokes circular ring.
So
Because I suspect in that case, there will be no infinite velocity.
yeah, it could be. So you
Like a
want,
parachute.
you want to put boundaries
Well, I
to
take
the equation.
I take a vortex sheet bounded by the vortex ring. So vortex ring is a singular boundary of the vortex sheet. Vortex sheet is just this continuity of velocity, and the vortex ring is a pole. I mean, it's not a pole, but with Euler. So in Navier-Stokes, nothing is singular. I mean, it is a.
And you want to do it with Navier-Stokes. You want to put boundaries, the vortex sheet, and
I want vortex sheet bounded in the Euler limit. It's vortex sheet like a disk, and the boundary of the disk is a vortex ring, which makes potential multi-value. There is a discontinuity of the potential across.
but you're telling me that using this scenario, we are not gonna see like infinite velocity.
In that case, I believe,
Okay.
I have some estimates, which will say that in that case, velocity will not be.
So recently I was asked by Grayer there in Princeton also maybe to have like a wall, and then you have boundary condition to have zero velocity, and then how this affect also.
That's right.
So you can have also this configuration and see how.
Velocity is fine.
I haven't, I haven't done the calculation in those, but it could be possible.
Is there any other question?
So what, if I look at the evolution of this in Navier-Stokes, I look at this vortex you have there, helical structure, what happens after a long time to it?
What we know is that the solution exists, but we don't know. We don't know exactly.
Is there a picture? Does it straighten out or does it do something nice?
I don't know.
It loses sense after the thickness becomes comparable with the radius of approximation.
But his question is more like if at the end you get you regularize
it will
more
dissipate, of course,
and dissipate, but how dissipate or how decay infinity.
So look, I haven't. It gets thicker and thicker as time goes on, and you're saying.
So no, when it becomes very thick, the approximation used to derive it no longer applies.
Okay. Yeah. But maybe because we have global solutions, one can ask if they decay in some way at infinity or how they behave when time is very big. But we haven't thought about this yet. So for example, there are results for perturbation of the Langmuir, you can have results. So you perturb with a more or less regular force around the vortex, the Langmuir vortex, and then you see that there is decay. There is a good decay also.
So in your last theorem, the expansion, so the thickness of that's actually prescribed. I mean, if you try to do some other, so you can compute actually the rate.
Yeah.
And if you try to do like, you can't change it.
No, it's possible to change it, but we got it. When we got it naturally and give us the heuristic of, because it's something compared with the result of Galais-Sverac for Navier-Stokes, starting with a circle. So they proved that for short time, they have the vortex filament binormal flow. They behave like the binormal flow equation. And then we were happy when we got this for Euler. So this is the Euler-Reynolds equation just in the half plane. So when you do this configuration about a donut getting thicker and thicker, and then you have an appropriate way of getting the Reynolds stress behave like this, and then you just say that the velocity square has to be of the order of how above the Reynolds stress, then you get immediately this ODE and then give you Euler Navier-Stokes heuristic.
Okay.
So this is the way we get.
But so that
But it's possible.
That mu is something that you can compute as.
Can be a lot. Can be a lot of different mu. This turbulence. No. This is no. This is not given by the.
Okay.
There can be there are infinite many.
Okay, but then you don't have like bounds. You can essentially achieve any number.
This is proportional to the amplitude.
Okay, so there is something there though.
Yeah.
Okay.
Yeah.
It's not like you can do everything.
No, everything. No, there is some freedom. But.
Got it.
Thank you very much. Let's thank again the speaker, and if there are more questions, you ask them at the go.